All right, so this talk is it's about quantum communication complexity, and that's something that I'll define later if you don't know what that is. It's about entanglement-assisted quantum communication complexity, which I'll explain, and then it's about the comparison between entanglement-assisted quantum communication complexity and EPR-assisted quantum communication complexity, which is an a priori weaker form of quantum communication complexity. Okay, and so, oh, okay, good. If you didn't hear what I said, I was explaining the title, which I'll explain again several times. Okay. Yeah, this is joint work with Aram Harrow, and who's a professor at MIT, and then it started while I was at MIT and as a PhD student, and now I'm a postdoc at the Institute for Quantum Computing, University of Waterloo. Okay. So for the experts in the audience, I'm going to state our two theorems on the second slide, and then I'll actually explain what those mean a little bit later. But for people who are experts, the two results that we prove are, first, we show a relationship between entanglement-assisted quantum communication complexity with arbitrary entanglement and EPR-assisted quantum communication complexity, and I'll explain what these are later if you don't know. And in particular, what we show is that for the bounded error versions of these, so when epsilon is a constant, I'll also explain the significance of epsilon later, these two are related up to a constant. Okay, so that's our first result. And then the second result is about the cost of state conversion. So it's about a task where two players, Alice and Bob, share an entangled state, and they want to convert their shared entangled state chi to another one, nu. So how can you prepare nu from chi? I'm going to call this nu. I think it's actually a different letter, but I'm going to call it nu anyway. Yeah, and how much communication Alice and Bob need to pass between each other in order to create the state nu from the state chi. And we both upper and lower bound this quantity. So we upper bound it by a sort of distance metric between the states chi and nu, which we define it. We call it the L infinity Earth mover's distance. So I'll say a little bit about it later, and I guess the significance of it is that it's relatively easy to compute from descriptions of chi and nu, whereas previous results could bound this complexity of state conversion, but the bound was difficult to compute from a description of chi and nu. And the other significance of it is that, in a sense, it is like a relaxed upper and lower bound. So, or if you make a relaxed version of the L infinity Earth mover's distance called the smoothed L infinity Earth mover's distance, then that is actually a lower bound for this cost. Okay, so those are our two results. The structure of the talk will be that I will start now by explaining what theorem number 2 means. So I'll try to explain the statement of the result if you've never heard of any of these things. And then I will return later to theorem number 1, explain what that means, and if we have time, maybe I'll say some things about the proof. Okay. So theorem number 2. This is about state conversion. So what is the task of state conversion? In case you don't know, so as I was explaining earlier, state conversion is a task in a setting where we imagine two parties, Alice and Bob, and they share this entangled state, chi sub AB. So, this is a state where some of the qubits belong to Alice, those are the A qubits, and some of the qubits belong to Bob, and those sets of qubits are entangled with each other. And Alice and Bob can communicate, but every time they communicate, it costs them, right? So they can communicate even qubits if they want, but every time they do it, it costs them. And we want to know, what is the minimum amount that they have to communicate with each other to convert this shared state into a different one. That's state conversion. Oops, sorry, wrong arrow. Right. So what's the minimum amount of communication needed? Okay. And we bound this quantity for a given state. So if you're explicitly given the descriptions of chi and nu, we bound this minimum quantity by what we call the L-infinity Earth mover's distance. So now I'll define what that is. Okay, so if you have two states, how do you get an estimate for how much communication it takes to convert one into the other? So we say, well, what you should do is you should start by writing out each state in the Schmidt basis. So you take the Schmidt decomposition where the bipartite split is between Alice and Bob. So this is chi written out. It has Schmidt coefficients chi sub I, and nu has Schmidt coefficients nu sub j. And then you plot, you make a plot of the Schmidt coefficients. Well, actually, you plot them against their log. And so this is a probability distribution because all the Schmidt coefficients sum to 1. And it's what it really is like the probability distribution of the random variable which takes the value log chi sub I with probability chi sub I. Okay, so this is a probability distribution. This is the corresponding one for nu. And we say that the L-infinity Earth mover's distance between state chi and state nu is how much effort it would take an Earth mover, so some entity which has to convert this distribution to this one by moving small bits of mass, right? So and in particular, how we quantify effort is in the L-infinity norm. So we say we want to know the minimum of the maximum amount of distance that this truck has to move any particular bit of mass in order to convert this distribution into this one. So for example, suppose the furthest amount that this truck had to move with any particular bit of mass was from here to there. Maybe that's reasonable. Maybe you can imagine an Earth moving scheme where that's the furthest move. Then if you imagine these two plots superimposed on top of each other, that's a distance of like that far, right? Because he had to move at this this position over here to this position here. Okay, so then if that was the furthest he had to move with any particular piece of mass, then this distance here would be the L-infinity Earth mover's distance between these two plots. Okay, so that's the L-infinity Earth mover's distance. And going back to our result, we're saying that this is a bound on the amount of communication complexity. And I'm just describing here the statement of the result. I won't describe the proof because even the proof of the other theorem may not fully get done, but because of time. But anyway, I guess essentially what we're saying intuitively is that if you want to think about the communication cost of state conversion, this is really the right, not basis, but the sort of the right way to present your data. And distances in this plot are really sort of the what matters. Okay. And then let me now describe the statement of the lower bound. And all I have to really describe for that is the smoothed version of the L-infinity Earth mover's distance. Oh, I should mention, there are a couple typos. Sorry, I didn't get a time to fix this because I added slides late. That's an omega, because this is a lower bound, so it's not an O, it's an omega. And there's another typo on the next slide. Here I'm defining the smoothed version of L-infinity Earth mover's distance. So there should be an epsilon up here, and it should say smoothed. Okay, so the smoothed version of L-infinity Earth mover's distance is exactly the same as the original version, except before you do this Earth moving process, you're allowed to change the original distributions you had by epsilon in the total variation distance. So. And then you're allowed to do this in such a way that it minimizes, like you get them as close as you can with your epsilon move, and then you have to do the rest by L-infinity moves. Okay, so that's the smoothed version. And the reason that matters is that the reason we have to put that in there in order to get a lower bound here is that the sort of method we use for lower bounding the cost of state conversion depends on the inner product of states, and it's possible in principle that one of the states has a little tiny bit of mass really far out, and you would have to in the L infinity norm you would have to move that little tiny bit of mass all the way back in, but that wouldn't actually change the fidelity very much in some sense. So you have to sort of account for this these annoying cases where you can have like a vanishingly small amount of mass that's really far out. And so the way we account for that is we say, well, you can just change whatever mass you want up to epsilon at the beginning. Okay. All right, so that's a good question. So the question was, if we're really worried about the amount of mass, little small amounts of mass that are far out, why don't we just change the L infinity norm to some other norm? What's that?
I guess the converse is sort of an answer to that, right?
I see. Yeah. Okay, and that's a result that I don't actually have in the that I don't actually have in the presentation. So I can't show it somewhere. But well, anyway, let me take that question offline so that I finish. But please bring it up again at the end. Thanks. Okay, sorry. So this is the statement of the result for Theorem 2. So that's our second result. And so now the rest of the talk will be about Theorem 1. Okay, so Theorem 1 is about quantum communication complexity. I haven't said what that is yet, so now I'll tell you what quantum communication complexity is, and then I'll get into saying what entanglement-assisted and EPR-assisted quantum communication complexity are. So the most basic setting for communication complexity in general, and here we're talking about communicating qubits rather than classical bits, is you always start with a function, and you're always asking the communication complexity of the function. So, and the function takes two in-bit strings and outputs a single bit. So the in-bit strings are x and y, and we're again imagining this setting where there are two players, Alice and Bob, and they can communicate, but every qubit of communication that they use costs them. So we want to count how many they use. And their goal in this case is Alice is given x, Bob is given y, and at the end we would like Bob to output f of xy, which is a single bit, correctly. Okay, and so the minimum number of qubits of communication required to do that is the quantum communication complexity of f. You can also talk about bounded error quantum communication complexity. So it's the same process. You're just allowed to fail with probability epsilon. So you can get the answer wrong sometimes. So that's for the rest of the talk we'll be talking about bounded error communication complexity. And now, okay, so this next slide is to define entanglement-assisted quantum communication complexity, which is the same task as before, except that Alice and Bob get an additional resource. Not only are they allowed to communicate single qubits after receiving x and y, but before they receive x and y, before the whole game even starts, they get to share this thing, an arbitrary entangled state of any dimension. So for the qubits that they communicate, we're counting the sort of total dimension or total number of qubits that they can communicate. For the shared entangled state, we're not counting. It could be, arbitrarily large. And if you've ever seen a non-local game, or if you've ever familiar with non-locality in quantum mechanics, the idea is that maybe they could use this additional resource. Well, it doesn't allow them to communicate. We know that, not in addition to the communication they already have. But maybe they could use it to somehow correlate the the information in their possession and gain an advantage for this task. So this is really and that in some sense is really the central question that this work is about. It's like, how much does having shared entanglement on top of quantum communication actually help you? Yeah. All right. So there's a natural analogy when you're talking about shared entanglement in quantum communication complexity. There's a natural analogy to classical communication complexity, which I guess I haven't defined, but it's the same thing as before, except Alice and Bob can only communicate classical bits. And this, as you might imagine, this was studied first. This was introduced later in analogy to this. And so there's a fairly long history of studying classical communication complexity. And maybe the closest, there really is no analog to shared entanglement, but maybe the closest analogy would be that putting shared entanglement into a quantum communication complexity protocol is like putting shared randomness into a classical communication complexity. So these are dice. This means that Alice and Bob get to share an entangled state before they start the protocol. This means that before they start the protocol, before they see X and Y, Alice and Bob can roll as many dice as they like and write down the answers. That's shared randomness. And it's known, there's something called Newman's theorem in classical communication complexity, that you can, for any given fixed function within input size n, you can bound the amount of shared randomness that you need to perform this protocol sort of within a small error of the optimal. And the bound is log n over delta, where delta is your error. So whereas maybe a priori you would need some enormous amount of shared randomness, maybe not arbitrarily large, but maybe like up to n, we actually know that you can sort of approximate the optimal thing with log n over delta shared random bits. So the reason I'm bringing up Newman's theorem is that in some way it is a motivation for what we were trying to accomplish in this work. So you could ask, do we know a similar statement about quantum communication complexity and shared entanglement, so the analogous statement? And so in other words, is there a quantum Newman's theorem? And that's the sort of, I guess the question really would be, in a protocol like this, where f has fixed size n, how much entanglement do you need to get close to the optimal, close to the optimal probability of success without having to blow up your communication too much? So this is not known. So this is just a big open question, and the one that maybe is inspiration for this work, although we don't resolve it. Okay. What we do instead is we say that if you start with a general entanglement-assisted quantum communication complexity protocol, you could simulate it with one where we still can't bound the dimension of shared entangled state that you need, but we can say that it's only EPR pairs. So in other words, instead of bounding the dimension that you need for your shared entangled state, we characterize the type of entanglement that you need. Okay, so this over here is meant to be EPR-assisted quantum communication complexity, right? And just in case anyone is confused, I mean, here's how the comparison between these, we now have three quantities really, but the comparison between these three quantities. It's there's regular quantum communication complexity with no shared entanglement, a little bit smaller because you've been given a greater resource. EPR pairs is a slightly larger resource than no entanglement, so that means that it will make the communication complexity smaller. You have more resources, so you can be more efficient, potentially. And then if you have arbitrary shared entanglement, you have even more resources than EPR pairs. Those are just a small subset of all possible shared entangled states. So that's even smaller yet. Okay, so now I can return to the statement of the main result. So this is EPR pair, EPR-assisted communication complexity, and this is regular entanglement-assisted communication complexity. And we show that for constant epsilon, these are related up to a constant, so they're essentially the same in asymptotic notation. And if you want epsilon dependence, then there it is. Okay, so then I'll mention a bit of motivation for maybe why this result was interesting to us. The first one is that there are known lower bounds for the amount of communication required to prepare an arbitrary shared entangled state from just EPR pairs. And so we know that it's expensive, if you had an arbitrary shared entangled state, we know that it's expensive to start with EPR pairs and just get to here first and then run this protocol. You could imagine trying to prove this result in that manner. But we know that shouldn't work very well. So in a sense, that's almost seems like it's in the opposite direction of our result. So, but what we show is that despite those lower bounds, there's some other process you can do where you start with a protocol like this, and you change it into a protocol like this, but in some other manner than just reproducing this state from this state. You have to use some property about the fact that this protocol only required small communication. So that's one reason that maybe this result is interesting. Another reason is that in non-local games, so I'm not going to say what a non-local game is, but it's like this setting here, except with no communication at all, so no blue arrows, only shared entanglement, and then both Alice and Bob report an answer. So Bob reports a bit, Alice reports a bit, something like that. In the context of non-local games, we know actually that bell pairs only sharing bell pairs can be strictly weaker than sharing arbitrary entangled states. So there are a couple works on this. I actually may be missing one here even, so this isn't comprehensive, but there are a couple places. One is the I3322 inequality or game, where it's known that arbitrary entanglement you can have a higher winning probability with arbitrary entanglement than with any number of EPR pairs. And there's also a result due to Regev to this same effect. Okay, so these are, I guess, some motivating examples, but nonetheless, we actually managed to prove that in the setting of communication complexity, these two are close to each other. The rest of this talk is about a proof of this theorem statement, and I think, I don't know if this is allowed, but I think it might be a good idea to take some questions here before we get into the proof, if that's okay. Yeah, all right. Are there any questions at this point? If not, it's okay.
Can I think of the game as just the same thing but without any communication?
Yes. So the question was, can you think of games as being roughly the same as this setting but without communication? And the answer is yes. The only difference really is that Alice needs to report an output as well. But that's it. Yeah. Any others? Okay.
Does classical communication in this context have a cost?
Yeah, it's the same. Okay. It's if you communicate one classical bit, we just say you used one qubit. It's also the case that when you share entanglement, arbitrary entanglement, we know that entanglement-assisted classical communication complexity and the same quantum communication complexity are related within a constant. And that's because if you share entanglement, you can always teleport qubits using classical communication. Yeah. Okay. All right, so those are all the questions. I have 6 minutes, maybe. So I'll try to say a little bit about the proof of this theorem. Okay, so so the general outline of this theorem is that we're going to start with a entanglement-assisted communication complexity protocol with arbitrary shared entanglement, and we're going to try to simulate it by one where you only share EPR pairs. And we're going to do that first by looking at whatever shared entangled state Alice and Bob have initially, which could be arbitrary, and we're going to chop it up into bins. So this is the Schmidt decomposition of the original shared state phi. And we're going to divide the Schmidt coefficients into bins based on their size. And these are like exponentially decaying bins. Okay? And to each bin, we're going to associate an unnormalized state. So this is like chopping this state up into bins. And of course, the sum of these states is the original one. And a fact that we will use later is that the Schmidt rank of each one of these smaller states, phi sub j is, the Schmidt rank is at most 2 to the j, roughly. And the reason for that is that phi sub j, its norm is at most 1, because it's like sub-normalized. And its minimum Schmidt coefficient is 2 to the negative j, roughly. And so 2 to the, it can have at most 2 to the j of those. All right. So this is the beginning. You take shared entangled state, you chop it up. Okay? And then this chopped up entangled state, you write the outer product of the original shared entangled state, but we're going to rewrite it in the chopped up form. If you remember this, phi is the sum of the phi j. That's the same as this statement here. Okay. This is a matrix. It's a density matrix. You can imagine writing that density matrix out. It might be the blue box, right? The original blue box. And the idea is that we would like to somehow replace, I should have said, this is the previous slide, the intuition for chopping this up into phi sub j is that each of these, because all their Schmidt coefficients are related by a factor of 2, they have what's called low spread. The spread is like the maximum ratio between any 2 Schmidt coefficients. And because they have low spread, you can imagine them as being intuitively close to a maximally entangled state, a collection of EPR pairs. Okay? So that's maybe the high-level idea, but then it's not so simple to chop up a state. The reason is because you get cross terms in the density matrix, right? So a phi sub, if I and j are far apart, this cross term still appears here. And the Schmidt coefficients in phi sub j are all about the same size, same with phi sub I, but the Schmidt coefficients between, the Schmidt coefficients of phi sub j are far from those of phi sub I. So this hasn't really gotten us anywhere. But what we can do is write out this density matrix as the blue box, and we can imagine trying to approximate that in some sense, maybe in the success probability sense, by a different matrix, which is where we just cut out this red band, and we delete all of the blue, and we just keep the red band. And the intuition here is that somehow that's removing all the terms, all the cross terms where I and j are far apart. Okay. But then the issue is that this may not be a density matrix, this red band. Okay. So actually, what would be even better is if we could do this. That would be a density matrix. And we're going to get there eventually, but it's going to take us a couple steps to get there. Okay, so we're going to go back to just cutting down to this here. And we would like to show that this chopping, just hauling off and chopping off all of these like far from the diagonal terms only causes small error in this communication protocol. Because I'm going to run out of time, the rest of the slides are, I just put the whole slide up at once. So start at the top and go to the bottom. Okay, so how can we bound? So we're trying to bound the error probability. So the probability that Bob outputs the wrong bit here. And well, you can sort of write this out algebraically as this expression, where C is some unitary that Alice and Bob are applying over the course of their communication protocol. All right, I'm at time now, and I'll use my question minutes because people already asked questions. Okay. Then the idea is that The idea is that then you can rewrite this expression, the sort of probability of Bob outputting B, as a sort of skew probability. We can collect all into one unitary, which is really the trace of the original shared state against some unitary P. And this unitary only requires roughly two qubits of communication for Alice and Bob to implement on their shared state. So we rewrite this in that manner. And then we use a fact, and this lemma is maybe the central technical takeaway from this talk. We use that, so what we cared about was the trace of phi against this unitary. And if you write out that trace, these terms show up here. And what we're interested in is the difference between the trace of phi against this unitary P and the trace of rho, the new bounded state against this unitary. That tells us how much error we've induced by chopping rho down like this. And this says that that error term consists only of cross terms that are far from the diagonal. And this lemma says that all cross terms far from the diagonal should be small when acting on a unitary which is implemented with only q qubits of communication. So this is, in a sense, like maybe the key technical nugget. If we have that, I'm just going to move quickly through the rest of this. That allows us to, how am I doing? Okay. Long story short, that allows us to chop into this banded matrix here without inducing too much error. How do you get to this from the banded matrix? There's this proof by pictures. You start out, well, that's still the band, and you can cut out one little triangle every 1/epsilon triangles and only induce epsilon error. So this is just like a total variation thing. It's not even about communication at all. So you can do this, and then there's a property of our result that actually you can now add in these corners back, and you get these squares, and then you can zoom out, and you get that. And each one of these squares is sort of close to a bunch of EPR pairs, and I won't say why that is, but it's true. Yeah, there are a few more steps, but I think I'll end there. Okay.
So we should take a couple of questions here.
My question is on state conversion. In
Yeah.
your protocol, how many rounds of communication do you perform?
How many rounds of communication? Okay, so the question was, in state conversion, how many rounds of communication are needed? Let me just think about this. I guess I don't... I mean, I think you could do it with one round from Alice to Bob and one round back if in each round you get as many qubits as you like. Yeah. But we're really counting the number of qubits here. But okay.
Okay.
Yeah.
And another question is how to calculate the infinity? Is it easy or generally difficult?
Oh, so it is just as, so I guess it's right, d infinity. So the question is, how do you calculate d infinity? This is going to take me a while to click back through all of these. I don't know how long, actually. But d infinity is just as hard or easy to calculate as the Earth mover's distance between two discrete distributions. And that's a good question. Oh, no, yeah, there should be a polynomial time algorithm for this. I don't know exactly the polynomial scaling. Yeah, and I can explain that offline, yeah. I mean, polynomial in sort of the size of the state. The size of the state could be huge, but yeah.
So in your theorem 2, you have an upper bound for preparing mu exactly, and then a lower bound for like this fidelity thing, but the lower bound could be way lower than the upper bound. Do you have an upper bound for the allowing some fidelity thing?
So you,
fidelity thing.
I see. You're asking how different could our lower bound be from our upper bound? Is that?
Well, I mean, as you pointed out, it could be very different, right?
Right.
But it seems like your upper bound isn't your upper bound for a stronger thing, because isn't your upper bound for preparing new exactly? No.
Oh, yes, that's true.
So the question is, do you have an upper bound for the case of preparing new to within order epsilon squared fidelity that matches the lower bound?
That matches the lower bound. I think they no, not that I know of. Maybe Aram should take that.
Well, you can always, I always forget how the trace distance and fidelity go, but like if you want an upper bound that achieves D, like the smooth D infinity, you can always throw away like epsilon mass, and then you have some infidelity, which is going to be either root epsilon or epsilon squared. Probably Mark can tell you. And so there's something like that would work, but like, we didn't work it out.
Right.
Okay, I think we have to actually end the session for lunch. But let's thank all the speakers and Matthew again for this talk.